Welcome to Chapter 10, Part 1. I do encourage you to watch the YouTube video that I posted introducing you to entropy. It's kind of a fun way to get started here. But now we're going to enter our chapter's discussion on entropy and that second law of thermodynamics. We are going to skip the insight at the beginning on recycling of plastics. It's an interesting read, though, if you've got some time. And we're going to talk about energy and nature and the direction of things. So we've talked a lot about bonds forming to minimize energy. And a lot of reactions and bond formations that you see in nature that occur spontaneously are going to lower the energy. But there's plenty of examples of processes that occur that are endothermic, where the energy of a system increases. For instance, we know at a threshold temperature, ice is going to melt. Right? This is an endothermic process that does happen spontaneously. So why? How will we know which changes nature will favor and which ones will need extra help? That's going to start us off with our discussion first of just defining spontaneity. A spontaneous process is one that takes place without continuous intervention. This word continuous is really important. That doesn't mean that it doesn't need to be initiated, and it doesn't mean that it's fast, right? So let's make a couple notes here. Spontaneous can be fast or slow. It also may need to be initiated. For instance, when you burn gasoline, right? Gasoline can sit in your tank or in your garage and not burn, even though it is in the presence of oxygen. But as soon as you add a spark, it will react, and it will continue to react until the reaction is complete without continuous intervention. So it is a spontaneous process. The example here about combustion of diamonds, this one's also thermodynamically spontaneous. But they are considered to last forever. Just because a reaction is very slow doesn't mean that it's not spontaneous. A non-spontaneous reaction is one that is going to require a continual input of energy, where maybe you need to add heat, and if you stop adding heat, the reaction stops. All right, so spontaneous versus non-spontaneous is about that continual intervention. Enthalpy and spontaneity are certainly connected. We definitely see that most spontaneous reactions, are exothermic, right? A delta H that is negative. But there are spontaneous reactions that are endothermic, as we have discussed. So enthalpy is related. There certainly is a connection, but it's not an exclusive determinant of spontaneity. So there's other factors at play here. We're going to talk about another thermodynamic quantity called entropy, and hopefully explain why that is, right, by the end of this discussion. Entropy is going to be abbreviated with the capital S, right? So enthalpy is H, entropy is S. This is another thermodynamic state function, right? Meaning that, right, so if we have starting materials and products, no matter what path we take to get there, that change in entropy is not going to be dependent on the path. It's just going to be dependent on the final state, right? Just like we saw with enthalpy. Now, historically, entropy was defined using something called the Carnot Cycle. The Carnot Cycle was introduced to kind of discuss and consider the efficiency of steam engines. The idea is that you have a system that can go through adiabatic and isothermal processes and can do work but be returned to its original state. So adiabatic means that no heat is exchanged. Isothermal means that your temperature is going to be constant. So the idea is that you have a system at an initial point that you can heat up, right? You can add energy to from a heat source, and there will be an expansion, right? So for instance, if gas is expanding in an engine, it's doing work on the surroundings. You can cut that heat source off. The gas will continue to expand, right? So that's the adiabatic expansion. You are not continuing to add heat, but it is continuing to work to a certain point. Then there's the isothermal contraction, where the surroundings will now do work on the system, which is going to cause the system to cool here, cause the gas to compress. Then once you, limit that, you go back to an adiabatic compression, you should be able to compress back to the original state. Now, this is a theoretical cycle. This assumes that there is no energy lost to like a waste heat transfer or something like friction. And so this tends to be an ideal scenario, not necessarily a realistic one. This essentially tells you the maximum amount of work that can be done. And it was used to define entropy as heat over temperature, right? So we're going to discuss that in more detail, but we're going to start off by thinking about entropy really broadly, right, as how we tend to define it early on, right? The degree of randomness or disorder in a system, right? Or chaos. Sometimes entropy is defined as chaos. So to do that, let's think a little bit about probability. When we think about a fairly simple example of probability, and we look at the rolling of dice. If you have one dice, right, the probability of rolling a 4 is 1 in 6. Now, if you add in a second die, I'm sorry if I do the plural of that incorrectly in this conversation. The probability of rolling 2 4s is 1 in 36, right? As you continue to add die, the chance of rolling 4s is only going to go up, right, exponentially. It's much, much more likely that you're going to roll a random set, right? What we're thinking of as orderly here is rolling all dice of one number. It's much, much more likely that you are going to roll all dice of different numbers, right? And we consider that your random set. The probability, it goes up exponentially, right, based on the number of die you have. So by the time you have 5 die, right, getting all of the same number in one roll is 1 in 1296, right? So that ordered system gets more and more rare. Now, if we think about the die as our molecules, right? When we look at even small systems, we are looking at huge numbers of molecules, right? Usually dealing in that 10 to the 23rd number of particles present. Getting a highly specified arrangement, right, rolling all 4s, is going to be increasingly hard to do, right? Statistically less and less likely. Statistical mechanics or statistical thermodynamics jumps in to add that we're not necessarily looking at how the molecules can all be arranged in just any order, but how they can be arranged, here we go, and give you that same energy, right? So a microstate, which is abbreviated with an omega symbol, is the way in which a collection of particles can give you the same energy. The number of microstates is going to increase as randomness of the system increases. So as the number of microstates increases, the amount of entropy in the system will also increase. Now, figuring out how many microstates are possible is not necessarily intuitive, especially with a scale of 10 to the 23rd particles. But there are some general things that we can discuss that can help us judge whether or not entropy or randomness or chaos is increasing or decreasing. So when we're defining that, and we're defining microstates, you want to think about that Maxwell-Boltzmann distribution we saw when we talked about gases. A temperature is going to tell us about the kinetic energy of our molecules, but not every molecule or particle is going to have the same kinetic energy, right? It's going to be a distribution. There are going to be some higher energy, some lower energy molecules. We're assuming right now that the system maintains the overall energy, but that energy can be transferred between molecules when they collide. It's going to maintain the same overall energy, but it's a new microstate, right? Different molecules are going to be up here in the high energy. Now, what can affect how many microstates are present? We're going to look at 3 different things that are going to allow us to make some judgments, make some predictions. Right? This is the connection, of course, mathematically or between entropy and the microstates. K is just the Boltzmann constant, and that's something that you would be given if you had to solve a problem using this equation. Like we said, as omega increases, S is going to increase. So if we're just looking at this qualitatively, how can we judge entropy? Well, let's start with phase changes, right? Phase changes as we go from solid to liquid to gas, we're going to see an increase in microstates, right? In the solid form, all of your molecules are locked into place and they only really have the ability to vibrate. So there's going to be much, much fewer microstates than once you melt and you go into the liquid state, where now the molecules can rotate, they can vibrate, they can move past one another, they can flow. There's going to be an increase in microstates as we go from solid to liquid. So we would say that the same system, once it has melted, would have an increase in entropy. Right? That's only going to continue to increase as we move to a gas phase. We break intermolecular forces. Molecules can spread out. They have more room to exist, really. And so there's going to be a lot more microstates there. And so as we melt or as we evaporate, entropy is going to increase. Now, if we go in the other direction, right, it's going to decrease. As the system gets more orderly, entropy would go down. Okay, so that's one way we can judge entropy without actually counting up microstates. Number of particles, right? So the more particles present, the more microstates you can have, right? So as we increase the number of particles, entropy is going to increase. So for instance, let's say you have a decomposition reaction where let's say 1 mole of A decomposes into a mole of B and a mole of C. Right? At the beginning, you have 1 molecule or 1 mole of molecules, but at the end, you have 2 moles or 2 moles of molecules. Right? The entropy is going to be higher now. Let me backtrack there. Entropy is going to increase simply because we increased the number of molecules. There's going to be more ways for them to be arranged to achieve the same energy. I didn't really leave myself much room here, but the last one is going to be temperature. Right? Let's say that we're looking at a liquid. A liquid at a lower temperature versus a liquid at a higher temperature is primarily going to have a difference in the Boltzmann distribution, right? At the higher temperature, you're going to have more molecules with higher kinetic energy, and there's going to be more varied arrangements that will give you the same overall average energy. So an increase in temperature tends to yield an increase in entropy, right? So we're going to be able to answer basic qualitative questions about entropy if we think about